Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is an introduction to the chain rule, one of the most important rules in differentiation within Calc 1. It is also one of the most abused rules within calculus, as there are a lot of places that students can make mistakes within this rule. Rather than jumping into the theorem itself, let's talk about a little prerequisite material before we get too far. It relies heavily on Leibniz notation, so let's go ahead and just review that really quickly. Let's see, Leibniz notation is this notation right here, d dx. What does that mean? Well, it means the derivative with respect to x. This is an operator. A linear operator is actually what it is. That's not that important as far as the linear part, but what is important is that you know this is not a fraction. Even though it's written like a fraction, it is actually not a fraction. Its finite version technically is. So delta y over delta x, that is technically a fraction. But when you get to the infinitesimal, d dx is definitely not a fraction. Although mathematically, I think a lot of people see that it works like a fraction. Please don't think that this is a fraction. It is an operator, just like addition is an operator, or subtraction, or division, or multiplication, right? All of those are operators. And nobody would say, well, you know what? 3, or maybe I should say 6 divided by 3. Well, that's the same thing as I'll go ahead and say the dots cancel. And so the dots cancel beautifully and it becomes like this. You can't cancel parts of an operator. That just doesn't work out. So this is totally not right. So you can't just pull pieces of an operator apart. You can't cancel these D's, for example. That's illegal. There's a lot of weirdnesses with Leibniz notation initially when you're a student. But as you work with it more and more, you'll realize that it is just like a plus sign or a minus sign or a division sign or a multiplication sign. It's one single piece and it tells you to do something. By the way, square root is just like that, right? You can't just take one leg off of it because, well, it cancels with something. So you would never do that. And so it's one specific piece. And if I said, this specific piece does something, you would say, yeah, I know what it does. It mangles that square root to turn into, or square root of 4, to turn into a 2. Just like d dx, the derivative with respect to x, of x squared, does some magic, let's just say, on that and turns it into 2x. They both do something to their, they operate upon their argument. The square root operates on 4 by returning the number you would square to get to 4, the positive number you would square to get to 4 technically. And d dx does something on its argument, which is the derivative. Now for this conversation specifically, I need to really get you to buy into something. The derivative with respect to x of y is that. So if I had a function y, I could take its derivative with respect to x by saying dy dx. I could also, for example, have a function called r, and I could take the derivative of that. If r was a function of x, I could take the derivative of that with respect to x. And in fact, if I had, for example, r is some function of time, let's just say r is 3t squared plus 1. It's some function that returns, who cares, some value, but you plug in a value of time, it returns some value r. And then if I have some other function, let's say f, that doesn't directly rely upon time, but instead relies upon r, let's say this is, I don't really care, 2r plus 4 or something like that. So we have one function that is a function of r, yet at the same time, r is a function of a completely different variable t. We would call this a composition. You could actually figure out what f is in terms of time if you wanted to, right? If I had both of these definitions, somebody walked in the room, they said, oh, hey, r of t is 3t squared plus 1. And then they said, oh, by the way, f is a function that relies upon r. It's 2r plus 4. Well, you could say, oh, did you mean to just tell me that f of r of t is equal to 2 times r of t plus 4, where r of t is 3t squared, 3t squared plus 1, and then plus 4. So notice what I'm doing. I'm substituting in, it's just a composition. There's no calculus here. I'm just composing. And so you could obviously clean this up and you can say, oh, that's the same thing as 6t squared plus 2 plus 4, which is 6. Great. Woo! Awesome, right? I've traded out f, which is a function of r, and turned it into a function, actually, of time. So f is both a function of r and a function of time because they gave me r as a function of time. It's my choice how I want to use it. But then it begs the question, what if somebody handed me f as a function of r and they said I need to find its derivative? Well, if this is all they handed me, then the only thing I could figure out is what is the derivative of f with respect to r? That's the only thing I could do because to me, this looks like a function of r. And of course, the derivative of f with respect to r would be 2 because that's the derivative of 2r. And obviously the derivative of 4, it's a constant, so that's 0. Great. But couldn't I have done this a different way? In fact, is there a different way to do this? That is, if all of a sudden somebody comes in the room and says, no, I don't think you truly understand. R is a function of time. And it is actually equal to 3t squared plus 1. And they say, no, I didn't want to know how f was changing with respect to r. I actually wanted to know how f was changing with respect to time. Now, how are you going to do that when f to our eyeballs is a function of r? And this is where the chain rule comes in. So the chain rule is all about nested functions or compositions of functions. Let's start motivating this with a very specific example. One factory converts sugar to chocolate using the formula C is equal to 8s. I'll write that down. The next factory converts chocolate to candy bars using the formula B is equal to 16c. You can see right now that B actually could be written in terms of S because C, the function that is the argument for B, is just right here. So I could just trade it in. I could say, oh, you mean B of 8s, right? So I could do that. But let's see what they're asking within this problem. Find the rate at which sugar is converted to candy bars. Well, this will help if I reword this problem a little bit. So let me go ahead and write out what I'm going to interpret this as. The rate at which sugar is converted to candy bars means we want the rate at which sugar converts to candy bars, right? The change, the derivative of S with respect to B, the rate of change of sugar with respect to how we're changing the number of candy bars. By the way, I think it's pretty legitimate for somebody to say, shouldn't it be the rate at which candy bars are converted from sugar? And I would say, yeah, that's pretty legitimate to argue that way too. They actually are the same argument, but let's just focus it this way. The rate of change of sugar, how quickly does sugar change into candy bars? So let's see. I'll start with the units on this. Now they told me that the units for candy and for sugar are in pounds. So this is, and C is for candy and B is for bars. So let's see, I'm gonna go ahead and write this out. So the units of this should be a rate of change of the pounds of sugar per pound, per bar. Okay, that's the rate of change there. Now let's talk about this. They didn't give us anything that directly relates sugar and candy bars. However, I could technically solve this equation for S. So I could say S is C over 8. So I could do that. And I could have sugar in terms of candy or chocolate, sorry. But that's a problem. We have sugar in terms of chocolate, not in terms of bars. The chocolate will be converted to bars right here. Chocolate is equal to bars over 16. So I first have to convert that sugar to chocolate before I can convert that chocolate to bars. I hope you're with me on that, but think about it mechanically. You start with sugar, you make some chocolate, and then once you have some chocolate, you make bars out of it. Okay, so we don't really have a direct unit conversion from pounds of sugar directly to bars. So we're gonna have to make a slight stopover, right? We'll convert those pounds of sugar first into pounds of chocolate. And then once we're done, let's see if I can spell chocolate correctly. Once we're done converting to chocolate, then I would like to take that chocolate and convert that to bars. Pounds of chocolate, and we're going to convert that to number of bars. Notice if I write it this way as fractions times fractions, it looks like, hold on, my screen always does that, I don't know why. It looks like we can cancel the words pounds of chocolate, and we would get pounds of sugar per bar. So it does visually make sense that multiplying these two fractions, these unit conversion fractions, will give us pounds of sugar per bar. In derivative notation, and specifically Leibniz notation, this is saying the rate of change of sugar with respect to bars is equal to the rate of change of sugar with respect to chocolate times the rate of change of chocolate with respect to bars. We're taking this stopover because sugar does not get directly translated into bars via our formula. Instead, sugar gets translated into chocolate, gets transformed, I should say, into chocolate. Then chocolate by another machine gets transformed into bars. So we have to convert sugar to chocolate and then take that chocolate and convert it to bars. This visual is actually the chain rule. If you have a function that's handed to you and you're asked to take the derivative of that function with respect to a variable that's not there, perhaps the variable your function is working with can actually be written in terms of a completely different function. Just like back in this case right here, we said, oh, we have a function of r, f of r, which is 2r plus 4. And then later on, somebody said, oh, by the way, r can be written as a function of t. And then they say, I want to know how your function f is changing with respect to t. If they had not told me that r is a function of t, I would not be able to understand their question. But luckily, they gave me this formula, r of t is equal to 3t squared plus 1, and I could say, okay, well, first thing I'm going to do is take the derivative of f with respect to the variable that f is defined in terms of. And then I will hop inside of f here, and hopefully that variable is defined in terms of t, which it is. So I'll take the derivative of that variable with respect to time, or t. And you can see here, mathematically or visually, it looks like these cancel. They don't. Remember, these aren't actually fractions, they're operators, but visually, Leibniz notation is incredibly powerful because it allows you to see that this will turn into df/dt if you visually say those dr's cancel. They don't, but visually it looks like they do. All right, that should be utterly confusing to you. It's totally fine. We will clarify as we move forward. So the idea of what happened in the last example can be visualized as follows. And I stole this from, and I'm citing the source, from the website, let's see, mathinsight.org. You have a function g and a function f. You're plugging in this value. Let's say this value is an x value, or no, let's actually keep it r. So you're plugging in a value of r here. Let me use a different ink, something that stands out. So you're plugging in a value of r into that function of g, and out pops some value. Okay, let's say that value that pops out is x. Now you're going to take that x and you're going to plug it into the function f and get out some value of y. That's the basic idea of a composition, right? Plug something in g, and g pops out some value, plug that value into f, and you get out some value of y. And this is mathematically what we're saying. Y is f of g of r. G is a function of r. It pops out some value, which we would normally call x, and then you plug that value in to f to get you a y value in the end. Scrolling down, you can see if you just fill in the labels, this tells us that dy, I have to zoom in here now, dy dr, because the circle was for r, is equal to dy, the derivative of y, with respect to the stopover variable, the intermediate variable, which is x, dy dx. Ugh, that black ink is no good here, right? And then dx dr, because x is a function of r. X, which is equal to g of r, is a function of r. So that's the idea of it. And you can see, again, visually, it looks like the dx's will cancel and you get dy dr. Again, both of these images are from mathinsight.org. I just want to make sure that I cite that so they don't get mad that I used it in this video. Now, unlike other videos I've done where I've done the theorems first and then gone back and then proved the theorems and then did examples, here it's probably better to start with just examples. Okay, so we're going to go ahead and start by taking the derivative of some compositions. So f here, we're going to take a derivative of that, and then we'll take the derivative of g. So what I'm going to do is hop into this. We know we want to take the derivative of f and g there eventually. We'll get to g in a moment. But the way I start these problems is redefining a function here really quickly. I'm going to let y equal, and we're going to go ahead and simplify this statement. Y is sine of u. So I've really simplified the statement where u is equal to that e to the x. Notice that they're both just base functions, very easy functions to take derivatives of. That's the point, is boil it down to easy functions. And it's a composition of easy functions. The outer function, I always think of these as like those Russian nesting dolls. If you don't know what a Russian nesting doll is, it's this thing right here, where you open up the big doll and there's the smaller doll within it. I think they're like called Matroska. I'm not going to even try. But anyway, the Russian nesting dolls. And so every time you open one, there's another smaller one inside of it, and you can just keep opening them up all the way through out that process. That's exactly what you're doing here. You have this outermost function, and you open it up, and there's a function inside of it. And you open that up, there's a function inside that, and so on and so forth down the line. So this right here is like our outer nesting doll, and then this is the doll that's inside of it. Okay. And what we're going to do is we want to technically, if y is equal to that sine, we want to take the derivative of y with respect to x. So I want to take the derivative of y with respect to x. However, if you look at y, it's not a function of x, at least it doesn't look like it. So all we can do is really take the derivative of that outer doll with respect to u, because that's all that outer doll looks like it's made of. It looks like it's made of the variable u, well, the sine of u, well, whatever. But then I see somebody gave me, when I open up that doll, gave me what u is equal to. It's equal to a function of x. So I'm going to go ahead and take the derivative of that u, maybe I should use a better lettering or coloring, with respect to x, because that's what u is a function of. And you can see the du's there look like they cancel. They don't, but it looks like they do. And so in this case, if I take the derivative of y with respect to u, we know from our derivatives of trigonometric functions that should be the cosine of u times, and then the derivative of u with respect to x is just e to the x. However, this is a mixture of variables, and you're not allowed to have a mixture of variables right now in calculus because you're in single variable calculus. So you have to replace that u with what u was originally defined to be. So this is going to be cosine of e raised to the x power times e to the x. That is the derivative of this function with respect to x. So df dx, which I called y, is cosine of e to the x times e to the x. Not bad. So let's go ahead and try the other one. Again, I'm just going to talk about it slowly and work my way from outside in. Often in mathematics, you want to work from the inside out because of the order of operations. But when it comes to the chain rule, you actually want to work from the outside in. We'll start by saying, let's go ahead and let y equal the simple outer function e to a power, where the power we're just calling u. And then u is just that power sine of x. Great. The derivative of g with respect to x, now notice what I've done there, it's the same thing as the derivative of y with respect to the variable it's defined in terms of. But then you have to hop inside that variable and say, well, do I know what that variable is defined in terms of? And yes, I do. U is defined in terms of x. So I'm going to take the derivative of that u with respect to x. So often it's much easier just to say, let this be y. So that you could say, well, dy dx, therefore, is dy du dx. It's okay. That's fine. And so if you did this, the derivative of this y with respect to u is e to the u times the derivative of u with respect to x is the cosine of x. Notice there's a mixture of two variables here. The u is not allowed. That was just a stopover variable that we created. So we're going to have to resubstitute in what u is actually equal for. U is equal to sine of x. So this is going to be e raised to the sine of x and then times the cosine of x. And that is the derivative of g with respect to x, or dy dx if you let y equal g of x. Now, all of that was in preparation for the actual theorem. The chain rule is a beastly theorem. It's wonderfully powerful, but it can be somewhat confusing, as you probably already can tell. So if g is differentiable at x, and if f is differentiable at g of x, then the composite function, f of g of x, is differentiable at x, and its derivative, so I use capital F to denote the composite function. So its derivative is equal to f prime evaluated at g of x times g prime at x. Now, you did not see me use that Lagrange notation in my examples because I think it's better to start with the Leibniz notation. So the Leibniz notation just says this. Hey, if I give you a function and it's a function of u, y equals a function of u, and u is a function of x, well then, dy dx is dy du times du dx. So this is the definition or the theorem that we were using this entire time. And actually, before I even start proving this, let's go back to the previous example and use the Leibniz notation, because I personally just use the Leibniz notation as we move forward. So it's probably a good idea to see that. So here we are back at the previous example, and let me just read this out loud because the language way of understanding it's much better than the notational. Even though the notational way is more rigorous, the language way actually works better for most students. So let me say this out loud. I have a function. It's a composition. So far, so good? Okay. I want to take the derivative of that function, which is a composition. Its derivative is going to be the derivative of the outer layer, evaluated at the inner, times the derivative of the inner layer. Think of this as an onion, or the Russian nesting doll, whichever. You're basically doing a derivative of the outer layer, peeling that away, and then taking the derivative of the inner layer. And this could go forever, by the way. You could have a function with 30 nests in it, so it keeps nesting and nesting. You just take the derivative of the outermost layer, evaluated at the inners, times the derivative of the next layer, evaluated at its innards, and so on and so forth down the line. So if I told you that I had a function, I'll write as y equals just for simplicity, and this function was e to the sine of x, well, y prime would equal the derivative of the outermost layer. So the outermost layer is e to a power. The derivative of e to a power is e to the power. That's what the derivative is. Normally, we would hope that power is just x, but it's not in this case. That power is actually the sine of x. And then, now that I'm done with that outermost layer, I zoom in to this blue inner layer and I say, got to take the derivative of that. So I'll go ahead and attach that via a link on a chain, the derivative of the sine. That's why they call it the chain rule, because you're adding links via multiplication to your derivative. And you can practice this all day long. Create any function. Well, don't create any function you want, but create functions, right? So if I said you had the tangent of x squared plus 2, for example, then y prime would equal the derivative of the outer layer. I will keep that green. Derivative of tangent. Well, that's a secant squared. But you have to rewrite the inner layer. It's the secant squared of the inner layer here. Not layer, but layer. So it's of x squared plus 2. And then now that you've taken the derivative of the outside, you're done with that. Take the derivative of this inside and attach it via multiplication. The derivative of x squared plus 2 is 2x. It's a very nice rule. So let me rewrite that. I use erasing quite a bit when I use the chain rule, just to illustrate that you took the derivative of the outer layer of that onion, and then now you take the derivative of the inner layer, and you're completely done. So I'll rewrite this here just in case somebody wants to take a look at that or take a picture or whatever they need to do. So let's go ahead and prove this. And I have to admit, the proof on this is going to be somewhat gnarly, but it has a lot of cool details to it that I hope you can pay attention to. So we'll start with what we're allowed to assume. We're allowed to assume that g is differentiable at x and f is differentiable at g of x. That's critical, so suppose g prime of x and f prime of g of x just both exist. That's the only assumption we have within this entire argument. It'll be incredibly helpful for us to give ourselves a roadmap. So off to the side, like any good mathematician would do, I'm going to write some scratch work that nobody will see when I'm actually proving this. I'm going to say what I want. Where do I want to go with this proof? Well, I technically want to show. And by the way, from this point forward, WTS just means want to show. By the way, we used to in mathematics write want to find, but WTF now means something completely different since texting started up. So we want to show the following, that the derivative with respect to x of f of g of x is equal to f prime of g of x times g prime of x. That's where we want to head, because if you look at our theorem, that's exactly what it says. The derivative of the composition is f prime of g of x times g prime of x. Now I'm probably going to have to write that in terms of limit notation, so I'm just going to note here that this derivative is equal to the limit as h goes to 0. We know the limit definition, I'm just writing it in here. F of g of x plus h minus f of g of x all over h. So we know that that's what that definition of the derivative is. Now that we stated what we want, it's very important for this proof to work to use the fact that we know if a function's differentiable at a point, it's continuous at that point. So I'm going to go ahead and mention that now. It's very, very important for this proof. So therefore, g is continuous at x because g prime exists at x, and f is continuous at g of x because again, f prime is f prime exists at g of x. But what does continuity mean? What does it mean that g is continuous at x? Well, normally, and I'm going to write this in blue because I'm going to erase it. Normally, when we say g is continuous at x, that would imply that the limit as x approaches, or I should say, I can't use x, I have to use something else. So I'll say, well, let's use x. Let's say g was continuous at a, okay? G is continuous at a. Normally, when you say g is continuous at a, we say that means the limit as x approaches a of g of x is equal to g at a. Okay. However, we're not saying g is continuous at a, we're saying g is continuous at x, and there's a different way I can interpret this, and I'll interpret this in black here. Let me leave that blue ink in there, and we'll ignore the fact that, well, that blue ink does not imply what I'm about to write, but I just want to showcase this. This implies the limit as h approaches 0 of g of x plus h is equal to g of x. That is, okay, if you look back over here, if g was continuous at a, that means as this input gets super close to a, it'll just equal the function value at a. The fact that we're saying g is continuous at x means as this input gets really close to x, that limit becomes g of x. It's the same statement. So now I'm going to erase the blue ink because I don't need it anymore, because that's not what that implies. So g being continuous at x tells me as h approaches 0, g of x plus h must actually equal g of x. And I'm going to grab that and move that over a little bit because I need a second argument here. And I'll say and then I'll fill something in here. Since f is continuous at g of x, as long as we let our input get really close to g of x, which as k goes to 0, that input totally gets close to g of x, the function will tend to f of g of x. That's because f is continuous because it's differentiable. We need those two pieces. And again, that's probably the hardest part. If you can get that, then we're pretty much rocking on the rest of this. The rest of this proof will be very, very nice and maybe not clean, but beautiful. Now, have we used all of our given information? The answer to that is no. We've supposed that g prime exists at x and that f prime exists at g of x. Great. And we've used kind of a lemma in a way that if you have differentiability at a point, you have continuity at that point. But we haven't actually used the definition of the derivative yet. So let's go ahead and also mention that. We haven't proven anything. We haven't even begun the proof. We're getting ready for the proof here. So this is all logical deductive arguments based on the fact that these two objects exist. Then we have continuity at x and g of x, or sorry, at g of x and at x and g of x for g and f. And now let's go ahead and write down the definition of the derivatives for both. So these two exist and are finite. Let's start with this one. G prime exists because that was part of our assumption. G prime and f prime at g of x both exist. G prime at x exists means that the limit as h approaches 0 of g of x plus h minus g of x all over h exists and is finite, by the way. And f prime of g of x exists implies the limit as, now notice I'm not using h, there's a very specific reason. H and k might be tending to 0 at different speeds, so I'm trying to be as rigorous as possible here. So the derivative of f at g of x is defined to be the limit as something is approaching 0, I just used k here, of f of its argument plus k, A lot of people want to know, why isn't this g of x plus k? It's not g of x plus k. It's actually f of the argument plus k. Wrong argument. It's f of this argument and then plus k. Remember, that's how the derivative is always defined. So the derivative is defined to be whatever picture this is, you'll evaluate your function at that plus whatever variable is tending to 0. So anyhow, that's why it is g of x and then plus a k. So anyhow, f prime of g of x is defined to be the limit as k approaches 0 of f of g of x plus k minus f of g of x all over k. So we have actually written down every little thing we possibly can concerning our functions with the given information. Now we have to actually start inventing or creating the mathematics or the proof. So looking over at what we want to show, we'll start by saying, well, the derivative with respect to x of f of g of x. Let's start with that. We're going to let capital F of x just be the composition, and we're looking for the derivative with respect to x of that capital F of x. And we know by definition that's going to be the limit as h heads to 0 of the fraction. I have to zoom out a little bit just because my pen will move the screen there. Of the fraction capital F at x plus h minus capital F at x all over h. That's just a stopover because I want to argue something here. This is going to equal the limit as h goes to 0 of, well, we can now trade out that capital F for a little f of g of x plus h. So just take that capital F there and plug in x plus h. We have f of g of x plus h. And then we also have minus f of g of x. The reason why I wanted to do that little stopover was because I made a statement a little while ago that the derivative of a function is defined to be the limit as k goes to 0 in this case of its argument plus whatever variable is tending to 0. And that is true. It's just this specific case that we're dealing with. Let me zoom out. This specific case right here, if I wrote derivative of f of g of x, it probably would not have hit home for you that the argument is not g of x plus h in here. It's supposed to be x plus h because our function is actually just defined to be this highlighted piece. Anyhow, that's a little confusing piece there, but I thought I'd just clarify just to write it cleanly like that. So that is the derivative that we're working with. We want to manipulate that now. We happen to know that since g prime exists, a limit as h approaches 0 of g of x plus h minus g of x over h equals g prime. This would imply, if I wrote that out in a different way, that g prime is equal to g of x plus h minus g of x over h. That's as h is approaching 0. I'm just writing that in language for a very specific reason. And like I said, it's a little bit hand wavy here. But if you were to multiply both sides by h, which is a naughty little thing here, you possibly should not do this. You'll get the following. And this implies that g of x plus h, as h, this is all as h approaches 0, is equal to, let's see, I'm going to move the g of x to the other side. So g of x plus hg prime of x. Again, this is as h is approaching 0. Now, this is true because g is continuous. And so because g is continuous at x, g of x plus h as h goes to 0 will actually become g of x. So as this h tends to 0 and that 0 times g prime, which is finite, disappears, the limit as h approaches 0 of g of x plus h should be g of x. Again, we have continuity, and that's why that's true. It's a slight bit hand wavy, but I justified it verbally at least. Therefore, or thus, the derivative with respect to x of our capital F of x, which is, again, that's the last time I'm going to write that. It's just the derivative with respect to x of f of g of x. yeah, that piece right there, is equal to, well, we have it written up here, but I'm going to trade out that g of x plus h for a g of x, let me highlight it, plus h times g prime of x. I squeeze that in there. And again, just reminding you, all I did really was I took this picture right here and replaced it with this stuff right here. Okay, nothing huge. Now what I'm going to do here is I'm going to go ahead and use the same argument for this f prime at g of x. The fact that we know f is differentiable at g of x. I'm going to use that same style of argument that I used right here. I'm going to use it for the derivative of f at g of x. So I'll write that in blue so you can see my argument. I've written it out. So as k approaches 0, because we know f is differentiable at g of x, f prime of g of x will eventually, as k approaches 0, equal f of g of x plus k minus f of g of x all over k. Now, again, very hand wavy here, but I'm still going to go ahead and use that same mathematics here, multiplying both sides by k, and that will be k f prime of g of x is equal to f of g of x plus k, and then minus f of g of x. Again, nothing super crazy here, but this allows for something nice to happen. We have, just by solving for f of g of x plus k, that f of g of x plus k, as k goes to 0, important to mention, that this will turn into f of g of x plus k f prime of g of x. Again, this is as k approaches 0. Now, something important here, because f is differentiable at, or I'm sorry, because f prime exists at g of x, it's it's continuous at g of x. That is, f of g of x plus a wiggle will eventually just become f of g of x. So that's important, and you notice here as k goes to 0, that will disappear. So we have continuity kind of supporting our argument there. And the last little argument that I need to seal the deal on this entire proof, and it's sort of on shaky foundation already just because of my notation, my hand wavy notation here. So this one specifically, as h goes to 0, this is all true, yada, 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 as h goes to 0. Not using limits there is a little bit dangerous. The argument's very solid, but I'm just letting you know that it's not really tight enough, but it's good for a description, a really like 90% description of the actual proof. The extra little 10% can lose a lot of people, so I just choose to do it this way. But the last little argument that I'm going to mention here is, first of all, we in this statement, we're talking about a k approaching 0, and notice that in our limit here that we're dealing with, which is for our derivative of f of g of x, we have h approaching 0. And that's a problem. Until we say, well, you know what? As long as something's approaching 0, that limit should be true. So what I'm going to do is allow k to equal h times g prime. G prime exists. We were told g prime of x exists. It's finite. It's just, it could be 5, could be negative 20, who knows what it is, but it exists and it's finite. So h times that as h goes to 0 still goes to 0. So we're going to go ahead and let k equal h times g prime of x. Again, g prime of x is a finite number. It's a constant. And so as h tends to 0, well, so does k, actually. And so we're perfectly fine. There's no issue there. And so I can trade out my notation here for the following. So all I did here was trade out, let me use a different highlighter. I've used that other highlighter enough. I've traded out the h times g prime for the k. Also, if you were to solve that equation right there for h, you would get k over g prime. So wherever I saw an h in my previous, basically right there, I'll replace with k over g prime. So now it's a like-kind exchange, we're okay. And if you evaluate this, this is equal to the limit as k goes to 0. This g prime will hop up to the top. And in fact, because it doesn't rely upon k, I'll park this g prime out front. We have I'll take baby steps here. F of g of x plus k minus f of g of x. And this is all over k. But again, we had just made mention, final highlighter here, that f of g of x plus k can be rewritten as that as k goes to 0. Only as k goes to 0. So we're going to do that now. K is going to 0, so I could totally do that. This is g prime of x times the limit as k goes to 0 of, instead of that f of g of x plus k, it's going to be f of g of x plus k f prime of g of x. And then we still have this minus f of g of x hanging off back, so I'll say minus f of g of x. And that's all over k. Now I just have arithmetic. F of g of x minus f of g of x, well, those cancel beautifully, and therefore we can cancel these k's, and you have the limit, so g prime of x times the limit as k approaches 0 of f prime of g of x. You don't see a k in there anymore, so that, it's just a constant. We're told that f prime exists at g of x, so that's just a number. Could be 5, who knows, but the limit of a constant is the constant itself, and so this is going to be written in using the commutative law of multiplication, f prime of g of x times g prime of x. And so we have successfully proven that the derivative of f of g of x is actually f prime of g of x times g prime of x. That is a tough proof, and a little bit of hand waving in there, but not too much, actually. I would say that's a 90% solid, maybe even 95%. QED, that is pretty awesome right there. Would I expect my students to regurgitate this? No, because that's literally what they'd be doing, is just copying what I just wrote down, and I wouldn't want that. So anyhow, let's go ahead. We'll stop the video now, and then in the next video, we'll use the chain rule to actually work with derivatives.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.